Okay, so I'm going to start the lecture to those select few who've come along rather than getting covered in foam. It's on covariance, correlation and regression. In a sense, it's all that I'll be saying in this module about bivariate data. That is, when you've got two variables that you're looking at. Okay, so bivariate data, it's normally obtained if you're doing correlational research, collecting two variables, and then you want to look at the relationships between them. Okay, and the starting point for it is actually covariance. So the core of bivariate data is looking at covariance, and then we can normalize it, standardize it, just as we did to get the Z-score, to get the normalized normal distribution. We can normalize the covariance, and we'll look at the non-parametric correlations. You've come across Spearman's rank correlation. In first year, we'll look at two other forms of non-parametric correlation, Kendall's tau and the Goodman-Kruskal's gamma. These are far more useful and appropriate if your data that you've got is from questionnaire style things, where it's essentially on Likert scales, ordinal data. Then we'll look at regression, which is really parameterizing and describing the correlation in a more formal sense. So you're actually giving it numbers rather than just saying, are they related? You're saying how. And then I'll just spend a brief time just showing you that actually ANOVA, and so therefore all of the stuff that I've been talking about up until today, is basically regression. It's how SPSS calculates it all. It's using the general linear model. It's always just doing regression. Okay, so often we want to know how things behave together, by which we mean, do they co-vary? As one changes, does the other tend to change in a systematic way? Okay, and that's the basis of correlational research. Okay, does level of depression relate to cognitive speed? So you take two measures, the depression measure and cognitive speed, some typically be a reaction time sort of thing, and then you correlate. You just ask, as one changes, does the other? Does family income and health status relate to each other? The answer to both of those, incidentally, is yes. Okay, so what we mean by covary is very simple. That as the value of one variable changes, the value of the second variable changes in a systematic way. Now, correlational studies, covariance and so on is a very small subset of that idea of systematic way. But what it means is that if we know the value of one variable, we can predict the value of the other. It's telling us something about the other variable. Okay. And so when they're not independent, that is when you can't use one to predict the other, then we say that they do not covary. Oops. So here are examples of variables covarying. That is, if you know the value of x, you can make a guess, an informed guess as to the value of y. So if x in this first plot, if x is a low value, the y value variable is likely to be high. It dips down and then comes up again. So you can make an estimate based on the value of x as to what you expect your second variable y to be. Here's another one. It's just a sort of oval shape. But if you know that variable is x is sort of between 8 and 10, y is likely to be small, roundabouts 4, or quite high, roundabouts 12. So they co-vary. There's a systematic relationship between them. These bottom two are the more standard forms of that, where there's a very simple, easy to spot linear relationship. In this case, as x increases, y tends to decrease, and the reverse here. Okay, so that's what we mean by covary. One of the things, and I'm sure you were told this in first year and second year, and you're getting it again, is that correlations, when things covary, there is not telling you about causality. And it's probably the most common misuse of statistics when you're looking at bivariate data, is to have an assumption of causality, that X causes Y, rather than there is a relationship which allows me to predict Y from X, to say something about it. Okay, so the sorts of things that are there, if you look at them in terms of do they co-vary, okay, the sorts of things that are there, and there's more examples, details in the handouts. The number of roads built in Europe co-varies with the birth rate in the USA. So, if you want to put a causal relationship between that, you've got some very energetic workers who are digging up and putting down roads and then whipping over to the USA, doing the dirty and coming back. Of course, it's a spurious relationship. Okay, and a famous case was Fisher again, who showed that there was a relationship between the importing of apples and divorce rates. Nobody would actually go, eating lots of apples causes divorce. At least I hope you wouldn't. Okay, and he did that, and it's a relatively famous paper, to show very clearly that there is no causality. You should never infer a causal relationship just because things co-vary. Okay, so my son loves playing on the latest, most violent games that come out on his PlayStation. Okay, so you can ask, do those with aggressive behavior like playing video games, or does playing violent video games make people more aggressive? And a correlational study will never distinguish between those two. Okay, you have to do an experimental study that is manipulate something so you ask the source of the cause and then see. Okay, so you just can't tell which way round these things go. So it's not reasonable to put causal. Now, of course, lots of people go with one particular inference from it because it makes news headlines, and you can make up a causal relationship. But it's just as easy to say those with aggressive behavior, like playing the violent games. I'm not saying what I think my son is. Okay, it's just reared its head again. A couple of years ago, there was a good deal of controversy about sexy videos. Now with Miley Cyrus and others just coming out again, you know, scantily clad. Is this inappropriate? Well, you've made an implicit model. Exposure to sexy music videos leads to underage sexual activity or some undesirable goal. But we could add the third variable. It's the most important thing to think about in any bivariate study, is the third variable problem. Can you explain your results not as you would like in a causal, simple causal relationship? Can you explain them by adding a third variable? So we can have personality traits of the child. Perhaps those that have a tendency to engage in underage sexual activity also like watching sexy videos. Okay, so maybe they're seeking out those videos, and that's why you see the relationship. Be a bit more controversial. Maybe it's to do with parenting. Maybe the way that the parents are acting and watching those videos, and then the child is still copying their parents, and it comes out that they're doing it, they happen to be underage, but that's, by the by, what they're doing is copying their parents. We don't know. At least I certainly don't. One thing that I do know, at least with my son, is that if I tell him not to do something, it at least trebles the chance that he'll go and do it. Okay, just by putting a barrier up there, he's just into teenage and is breaking the barriers. It's what he should be doing at his age. But maybe actually all of this publicity about it, making it sound dangerous and exciting, is what's going to encourage children to seek out the sexy music videos. Maybe it alerts them to the idea of sexual activity. And so, in fact, the press might be backfiring on themselves. There's all sorts of possibilities. In other words, anything where you see covariation, as one variable changes, another one does, automatically get in the habit of just going, it's a third variable. What could I put in? A common mechanism or process that drives both those variables that I'm actually measuring. So a third factor that feeds into it will give you covariation, but it's not the causal relationship between the two variables. Okay, so when you see correlations, start playing devil's advocate. Think of other ways that you could get the observed data rather than going for the simple causal relationship. Okay, now, the problem that we have is that statistics cannot do anything other than tell you if the observed relationship is by chance or not. Okay, so it can tell you how likely it is that the observed relation occurred by chance. It cannot tell you or solve these higher level conceptual problems. It's not designed to do that. In fact, it can't do it. It can't distinguish between a causal, spurious, and common process relationships. Okay, all it's going to do is tell you whether it's by chance. And again, what you see so often in scientific papers is people having an implicit model and then talking about it as though their data is supporting it, okay? Or just going straight for a causal relationship, being explicit about a model, and their data says nothing about the causal relationships. So be wary about covariance. Okay, what we really mean in terms of the statistics is looking at the linear relationships, that is, of those four, these two. Okay, and what we're saying is that when the value of one variable increases, so does the value of the second variable, or that it decreases. Okay, but we're only looking, and statistics only deals with these linear cases. It's not true, you can do more complex models. What that amounts to is some variables have high and high values and some have low and low. What do we mean by high and low? Well, as always, we're going to make it relative to the mean, the center point. So a high value is just something that is bigger than the mean, and a low value is something that is less than the mean. Okay, so we really are talking high, high, low, low. It's as simple as that. Okay, now we've got to think about a little bit of maths. It's not complex maths, I promise you. Okay, so high is when the observed value is greater than the mean, and low is when the observed value is less than the mean. That means high values are greater than 0, positive, low values are negative. So if we just take that idea and just put the -1s for simplicity, what we have is that low, low and high, high are always positive values. -1 times -1 is 1, and 1 times 1 is 1. Okay, so if you've got lots of situations where you've got low lows and high highs and add them up, you'll end up with a big positive number. The opposite, so when one variable is low and the other is high, you've got a negative and a positive multiplied, which is negative, or the other way round. So they're always negative. So if you add those together, you end up with a big negative number. So if you've got data where you've got lots of low, low and high, high, like that, you end up with a positive score. If the slope is the other way, if they're high here and come down, you end up with a negative score. Okay, so there's a way of splitting these things, dividing them by the mean, going to high and low, which will lead to numbers which are either positive or negative. Okay, and so what we do for covariance is exactly that. We take the difference of the observed value from its mean for one variable and the second one, and just multiply them and add them. Okay, so that's all that we're doing in calculating the covariance, is taking the sums of what's called the cross products. The product meaning multiplication, crossed between the two variables x and y. The reverse, you've got high, low and low, high. So the sum of those cross products will be negative. Okay, so the sum of the cross products is the core of covariance, and it captures the idea of if one variable increases, the other will either increase positive correlations, positive covariance, or decrease a negative covariance. What we want in all of these sort of statistics, of course, is the expected value of it, what it should be. We're trying to estimate the population parameter. So rather than the sum, we need to divide by the degrees of freedom rather than the n, just like we do with the variance, so that we get the unbiased estimate of it. We're dividing by the degrees of freedom. We are dealing with pairs of data, an xy pair, and so what we have is degrees of freedom of n minus 1. It's exactly analogous to variance, but rather than the numbers being single, they're now a pair, a little vector, two numbers. Okay, so we can calculate our mean as the mean xy rather than the two separate means. Okay, so the covariance is the sum of the cross products divided by n minus 1, the degrees of freedom. Again, just to point out, you don't have to remember these formulae. They're done by computer these days. It's just a short, convenient shorthand way of showing you what's going on. Okay, the trouble with covariance is that it captures only this one pattern, this linear relationship. So when you're calculating something like a covariance or a correlation or a regression, in fact, the most important thing to do is to look at the scatter plots. So here the covariance is minus 0.38 or minus 0.3, essentially 0, but there is a relationship here, most notably here. Here the covariance on the same scale is 3.5 or minus 5. Okay, so covariance doesn't tell you that there isn't a relationship, it says that there isn't a linear relationship. So you have to plot your data to check if the measure of covariance makes any sense. If you see a plot that looks like that, you know that its covariance is going to be close to 0. But it doesn't mean that there isn't a relationship. It means the relationship isn't captured by the covariance. Okay, so covariance in and of itself is not sufficient to say that the values are independent. If they're independent, covariance will be 0, or very close to. But a covariance of 0 does not imply independence. Again, when you're reading papers, you will see that sort of relationship is inferred or stated explicitly, and it shouldn't be. It means that there isn't a linear independence, the straight line that goes through them. Covariance is size sensitive. It depends on the scale. So the value that you get for covariance will change quite dramatically if you measure, say, height in centimeters or meters. The covariance will change. Okay, and exactly the same way with the idea of just a normal distribution. Doing anything with it because there's an infinite number is very hard. There's an infinite number of them. What you want to do is standardize them, normalize them, so that they become scale invariant. And we're going to do exactly the same as we did. For the normal distribution, we can take the z-scores, because that makes each variable have a normal distribution, or the same shape distribution, with a mean of 0 and a variance of 1. That means that the covariance is now also standardized. We call this the Pearson's product moment correlation coefficient. Pearson's correlation. All they've done is taken the original data, z-scored it, transformed it, and then calculated the covariance. Okay, so there's rho is the population value, analogous, if you like, to the mean being mu. There's a population value, and we estimate it with r from the sample. But it's just the covariance of the standardized scores. Okay, so here r is 0. You increase it slightly to 0.3. That still, to me at least, looks like not much of a relationship. By the time you're about 0.6, you can see something, and 0.9 is very clear. So this value of r will vary between -1 and 1. We've standardized it. And in this example, I'm just showing you the positive correlations. Okay, as a rule of thumb, and as a rule of thumb it is of course instantly violated, if you want to describe the strengths of correlations, of the relationships. This is one of the many tables that you will find saying how to deal with it, with values in the up to 0.2 being very low and above 0.8 being very high. I don't actually think that that's very useful because it depends on your expectations. So if I'm doing some modeling of the properties of neuronal responses, I am looking for correlation coefficients above 0.99. Otherwise, I don't think I've captured what's going on. If you had a correlation of 0.99 in a social science study, it would be the highest that has ever been obtained by a huge margin. It really is a rule of thumb. But don't stick to it. Think about how well you think you should be able to explain the data, and then work from there. So use the idea of these scatter plots, looking at those to say how good a relationship is it. Incidentally, this is the typical sort of value that you will see in psychology journals. It's really quite poor. What we can do in the same way that when we normalize a Gaussian distribution, a normal distribution to z-scores to read off the significance, but then when we have a sample, we go to a t-score. In this, we've done two estimates of variance, of variability, one for each of the samples. So we use, as we would for a single one, a t-score. Okay, but we have to do a little transformation of it to work it out. Notice that now, in correlation, where degrees of freedom are n minus 2. Because on this, we've had to calculate separately the two standard deviations to do the z-scoring. And that's where we've lost our degrees of freedom. Okay, there's a little formula there. Again, you don't need to know it, but just so that you can see it's still related to normal distribution z-scores to t-tests. So is bivariate data for exactly the same reasons. Okay, when we calculate a parameter like the mean, we've gone through how we can describe its variability, the standard deviation of it, the standard error of the mean. We use those to calculate our confidence intervals as well. Whenever we make an estimate, it is always good to give those intervals. With a mean, it's simple, it's the standard error. The distribution of the correlation coefficient, because it's bounded at -1 to 1, can't be outside of that, is going to necessarily be skewed. So if the population parameter is 0.8, the blue line, the distribution that you would expect to see from your samples looks like that. If it's -0.5, it's skewed the other way. The only time when it's not skewed is when the population parameter is 0, when they are uncorrelated. Okay, so we still want to have confidence intervals. And again, we resort to Fisher because he worked out how to do it. And the t-values, and using them, only applies when the correlation coefficient, the population parameter, is 0. Okay, and if we have non-zero values of correlations from our estimates, we don't know, we can know how likely it is that they're 0, but we don't know that if they're non-zero what the distribution is going to be, except it will be skewed. Okay, so what we're going to do is Fisher's transformation. To do that, we transform the data, transform the correlation coefficient into, let's call it transform space. We do all our calculations there, so if we've got lots of correlations, lots of different estimates of a correlation coefficient, we can transform them, take their average, and transform back. Once we're in transform space, we have, even for a single value, we have the mean of it. And so we can calculate the standard error of the mean in transform space and then just shift it back. Okay, so if we start off with our distributions and transform it, we end up with 3 distributions. In fact, the standard deviation, the variance of them, depends only on the sample size, not the value of the correlation coefficient. So we can calculate meaningful confidence intervals here because these are all symmetric, and transform back. What we end up with is an asymmetric confidence interval, or standard error of the mean. So you can't just put correlation coefficient plus or minus. You have to put the range in which the confidence interval spans, the standard errors. But it is asymmetric. That means that the estimate is never above 1 or below 0. And you can see here with rho of 0.8, quite a marked asymmetry in the confidence interval. It's symmetric at 0, and asymmetric again as you get away from, in this case, negative correlation coefficients. So just because it's a correlation coefficient, just because we're reporting an R, doesn't mean that we shouldn't report standard errors of it, the equivalent of the confidence intervals. Let people see how precise your measure is when they're reading the results. As we've talked about with ANOVAs, we need to talk about effect size of correlation. So this plot shows for 3 alpha levels, 0.1, 0.05, our standard one, and 0.01, the critical value of the correlation coefficient. So as you get to very large numbers, and these are the sorts of things which are often used in demographic analyses, you need only tiny values of R to be significant. Things where in fact the relationship is very, very weak, but still highly significant. Okay. So what we need is a quantitative measure to describe how strong the relationship is. So that rule of thumb we can convert into a number that makes sense, and we use R squared. R squared is the proportion of variance that one variable explains about the other. In ANOVA, it's the eta squared, or the R squared of the overall ANOVA model, with a big R there because there's more than one predictor in it. So what we should have as a reporting is the R equals the p-value and R squared. Do the R squared. If you want to be complete, you put in here confidence intervals, typical one being 95%. To do that, you have to do this transform and back again. SPSS can do that for you. Okay, so covariance. It looks at this relationship between two variables. That's the core of it. Okay. It says nothing about causality. Just measuring two variables and showing that there's a linear relationship between them. Just says there's something going on. The best way, the most sensible way of thinking about it is to put in the third variable. Think of a way in which you could get the relationship without having the two having a causal link between them. And remember that if the covariance is close to 0, if the correlation coefficient is non-significant and close to 0, it doesn't mean that the values are independent. It means they don't have the linear relationship. So look at the scatter plot. Whenever you have data of any form, find a way of representing it graphically so that you know what is happening with the data, and then deal with the statistics. Don't believe the statistics over your data. Okay, Pearson's correlation. It's the normalized covariance. All we've done is taken the z-scores of both variables, so we've standardized the variables that are going in, and that gives rise to a variable, a statistic, a correlation coefficient, which is bounded from -1 to 1, so you can't get a value outside of that. And other than in one instance where the actual population correlation is 0, will give rise to skewed distributions. So use Fisher's transformation to get the confidence interval and give the effect size. I know it's only squaring the R value, but it's a non-arbitrary value that has a meaningful interpretation, the proportion of variance in one variable that you can explain by knowing the other one. So how well you can predict the second variable from the first. All of the stuff I've talked about so far is on the assumption that the data is on a nice continuous scale. Now actually, it's a little bit more than that. It's on a continuous scale, and not that the variable is normally distributed on this scale, but the error term, and we'll come back to it in a minute in talking about regression, is normally distributed. If your data is not of that sort, then you have to do a different technique. With categorical data, you can use contingency tables, you can use chi-squares, and the idea of a correlation, of a relationship, doesn't make sense. Ordinal data does make sense. And it amounts to, if the rank now of a variable increases, does the rank of the second variable increase or decrease? Okay, so Spearman's, which you've come across in the first year, you rank the data within each variable and then perform a Pearson's correlation coefficient on the ranked data. Okay. And it's a very good way of dealing with skewed distributions and outliers. Okay, but data collected on a continuous scale. Okay, because the underlying assumption is that you're ranking a series of measures on a continuous scale, and it's really not very good if you start off with chunked data. By chunking, I mean that you force participants to make a very limited number of responses. So the typical things that you see on questionnaires like at scales. Unfortunately, Spearman's is often used in those situations, but it's not really appropriate. Kendall's tau is a much better idea. Okay, and rather like the difference between a sign test and the Wilcoxon signed rank tests, that idea of increasing the power by taking note of the size of differences, this is doing it in reverse. Spearman's is using size of difference. Kendall's tau is just saying, do they go up or down? It's putting everything into, if you like, those minus ones and ones before adding them together. So you have a pair of values, and the concordant pair is as x increases, y increases. Doesn't say by how much, just is there an increase? And a discordant pair, as one variable increases, the other value decreases. So here's a concordant pair. So any pair where it goes up, so from here to here is a concordant pair, as is from here to here. It doesn't distinguish between those two, even though in terms of the score, they're very different. So it just says x1 and x2, x1 is less than x2, and y1 is less than y1. Or you can reverse the ones and twos around. So you're just looking for every pair of data points. Is it concordant or discordant? Those are the discordant ones, where now you've got that a change of sign is how I think of it. If x1 is less than x2, if y1 is bigger than y2, so it's higher, then it's a discordant pair. Okay, so Kendall's tau you can adjust for ties, we'll come to that in a second, but it doesn't work very well when you have lots of ties. So when a tie data is neither concordant or discordant, okay, and it's better in that case to use the Goodman-Kruskal gamma correction value, which is the contrast between the two, the difference over the sum of the numbers of pairs. Okay, so if you've got data that you've measured on a continuous scale, but it's not normally distributed, it's very skewed, use Spearman's. If you've got data where there aren't that many ties, that many values where they're the same in both conditions, then use Kendall's tau. If you've got lots of ties, use the Goodman-Kruskal gamma. Okay, these corrections for Kendall's tau to the number of ties doesn't quite work as the number of ties increases. Okay, so Spearman's rank the data within each variable, calculate the Pearson's, and it assumes a symmetry of rank in exactly the same way that the Wilcoxon signed rank tests assume symmetry of rank for exactly the same reasons. Using the techniques of discordant pairs, because it's not using the magnitude of the difference, is going to be less powerful at detecting covariance correlations which are present, okay, but has the advantage that it deals much better when you've got ties in it and that you can't be sure of the symmetry, because it doesn't take account of symmetry of distance, of magnitude. Okay, Kendall's tau, the adjustment for ties will happen automatically in programs like SPSS. It's not suitable if you've got questionnaire data with typical Likert scale. If there's only 5 possible values of responses, then you're only detecting on it big changes. Okay, and then you want to go, you'll have lots and lots of ties in the data between your 2 conditions. Then you should go to the Goodman-Kruskal gamma to look at it. Okay, regression. The correlation just gives a size, as does covariance. Okay, often we want to be far more precise than that, and we want to say something really about not just the strength of the relationship, but what it is. How does one variable change with the other? Okay, so in correlations, covariance, you've got the sign, but that's it. Okay. So if you were going to try and describe bivariate data, the first thing you do is you plot out the scatter plot. Okay. And if there's no covariance, it's just a random scatter, the best way of describing it, because there's no relationship, is just the means. You've got the means and some variability about those means. So essentially, what you'd say is that the relationship y does not depend on x, it's just the mean, with some variability about it, which is putting a flat line that passes through the mean. If there is a relationship, what you'd want to do is to still go through the mean, but now have a line that has a slope to it. Okay, and what we mean by quantifying the relationship is just saying what that slope is. Okay, so we're going to have a line that passes through the mean, that's of the pairs, the xy mean, and has a slope. If the covariance is less than 0, the slope will go the other way. So the slope will have the same sign as the covariance, but it won't be the covariance. It's going to be a slope. Okay, so to do that, we have to go to the stage of now we're going to do a formal model. You'll actually see that ANOVA's every statistic that we do is building a formal model of what we think is happening in the world. We've got our y value is some factor of x, that's the slope, and a constant. Okay, so we're going to describe the data with a straight line. And if we ignore the error term for the minute, it's these two. It's the slope and the value when x is 0, often called the constant. So y equals ax plus c is a standard way of doing it, where c means a constant. It's actually a value when x is 0. It needs to go through this mean point, okay, and what that actually does is allow us to set the intercept. The intercept, b0, is the mean minus b1 times the mean of x. Okay, so everything actually depends on what the slope is going to be. So what we need to have is a way of saying what's the slope. How are we going to estimate what the slope of the relationship is? Okay, so the slope is just the ratio of how much y increases for an increase in x. Okay, so you just take, for a given increase in x, how much does y increase, and divide the two. Okay, so the slope is the amount you would expect the independent variable to change in the predictor. Okay, so a good slope, what do we mean by that? If it's a right that looks value, if the value is good, we'll have the data near to the line that you're using, to that predicted line. and a bad slope, the data will be a long way away from it. So what we want to do is estimate distance. Distance has plus and minus. The way in statistics we get rid of that is square it. We actually use the variance of the data about the slope, about the line. Okay. So here are 3 data points and the distance from the line to those data points. That's when the slope is 0. We can change the slope. This case, the distance has increased. This one has decreased and this one has increased. Okay, so all we're going to do is just take these distances, we're going to square them so that they are all positive values, and add them up. Okay, so this is how we do it. We now have to use an estimate of the y, that's the value of the slope at a given x. So it's that point there, that point there. It's our estimated value of the dependent variable. We then just calculate the sums of squares of it, the distance from the observed value to the expected value, square it, divide by the degrees of freedom. Okay, so we have a variance as our error term. Okay, and we use that error term, that variance, as the metric to say how good the slope is. How well have we fitted it? And what we want to do is make it as small as possible. So you'll often hear people referring to regression as least squares. Okay, what that means is that it's looking and minimizing this variance measure. So here you can see for different slopes, the variance. And as the line increases, or as the slope changes, the variance decreases and then will start to increase together. So we want the minimum value, the least sums of squares, the least squares, and that's going to give us the slope. It'll be the best fitting slope when we define it as having the least variance about it, the least error term. Okay. Now, thankfully, people have worked that out for us. We don't have to go through that trick of going through each possible slope and finding where it is. We can do it in one go, a one-stage analysis. Any linear system can be done like this. If you can't, so with more complex regressions, you have to find ways of estimating that error term, and then you just hone in on values which minimize it. But with this, with linear regression, we can do the calculations. It turns out it's the covariance divided by the variance of x. Okay, again, you don't need to remember those formula, but just so that you know that it really is looking at a standardized form of covariance again, but now you're looking at it by dividing by the variance of x. Okay, that gives you the slope. Okay, the effect size of regressions. Okay, so if you think of the y variable, sometimes it's convenient to think of it as a dependent variable if your x is a predictor. So if you actually have a formal model, you can think of it in terms of a predictor, an independent variable, but a predictor, and your dependent variable. More generally, it's just an x and a y, just 2 variables. Okay, and we can calculate the variability, the sums of squares of y. So they're represented by that circle. Okay, it's just the difference from y from its mean squared. We can calculate an error term, which is the y minus the estimate, and that's that area there. The sums of squares of the regression is the sums of squares of y, that total area, minus that, so it's that little bit here. Okay, and then we've got an r squared of the regression, which is this bit divided by the total. So how much of the variability in y have we explained for using the predictor? Okay, and this should be, you should hopefully be going and remembering that this is incredibly similar to the Venn diagrams that were up for ANOVA, because it is exactly the same idea. How much of the variability in our y in our dependent variable can we explain using our predictor, using this other variable. Okay, so because we've got, with least squares regression, we've got the error term variance and the regression one, and the variabilities of everything, we can calculate the significance of it using the F ratio. Now you'll sometimes see that people talk about linear regression and you can do the same thing using the t-test. But of course the t-value is just the square root of the F ratio. Okay, in general it's an F ratio where we take the variability of the regression divided by the variability of the error term. And in this case I mean by the sums of squares. So we're just doing an F test on it. Okay, to tell us about the significance of the regression. If you remember the correlation coefficient, t equals the r square root r over df, that little equation, it's the same as this, just in the t form of it. Okay, so we're going to use F ratios to deal with regressions. The reason for doing that and making the change is that when we come to more complex regressions, multiple linear regressions, lots of predictors, which Peter will cover in 3022, you use because the F ratio because the T1 doesn't hold. There's more than two values you've calculated. So correlation you can use for exploratory and descriptive values, descriptive cases. It can be used in explanatory, that is trying to build a causal relationship, but it's very weak because it just says up or down. Regression allows you to make these predicted values of y. Okay, so you can use it to check on explanatory explanations, to check on causal relationships, but of course you have to build the model first and then ask how well it fits. In all cases, there is the third variable problem, that even what you are assuming to be a causal link in your model could still actually be due to a third variable, something else. Okay, so a lot of the time my research is actually asking about third variables. Are there alternate ways of getting the same sets of results that do not have the causal relationships that we assume to be in there? And in fact, all of the projects that you're looking at in your afternoon sessions are of that sort. We're actually trying to find things where traditional explanations don't hold. Yep.
Is there a way to look at all three variables together, or do you have to look at the relationships separately?
At all.
If you had a third variable, could you look at how that?
Yes, that's the multiple linear regression. So you still have the idea of predicting a single value, but you have lots of predictors. And then it's just adding those in, you know, it was y equals b1x plus b0. Well, you can put in b2 z and b3 times another variable and so on. So you can just build up those models and do exactly the same thing, but instead of it being a straight line, when you put in a second one, it's a surface. So it's like a sheet of paper, and then there's the slope of one. It might have a slope like that. Yeah, so you just build it up. The methods for doing that, they are all essentially the same. As I said, Peter will cover them. Okay, so just want to quickly go through ANOVA as a regression. Okay, because if you think of what I've been saying, we're looking in ANOVA to see if knowing the level of the factor, the independent variable, explains variability of the dependent variable. Okay, and that really sounds to me the same as looking to see if knowing the score of an independent variable explains variability of the dependent variable. The only difference being it's a level of a factor or a score of an independent variable. Okay, so what we actually are doing in ANOVA is this, and we're converting our level of the factor to a score. So there's three levels of an ANOVA, A, B, and C, and there's the data points around them. Okay? So what we can do is plot these as a function of the level mean. We convert A into the mean of A. The B's, each one has a mean of B, and C, each of these has a mean of the C values. So all I've done is just replotted them by transforming a level of the factor into the mean of that level. So these values will be the same as, set to be the same as this. So the mean of these guys is all the same. This should be the same on here and here. It should have a slope of 1. Yeah, because the mean of all of these ones is, say, there, but that's going to be, by definition, this value here. The mean of all of these ones is about here, which is, by definition, that point there. So I've forced them to have a slope of 1. The only question is that slope significant? And the answer on this, the r squared is 0.445. That will be significant. Okay, that'll have a correlation coefficient that's quite high, the square root of 0.4, whatever that's going to be. 0.8 goes to 0.6, so it's about 0.7. That's 0.49, no, 0.6 something. Okay, and this is literally how SPSS is calculating your ANOVAs. When you put in an ANOVA with your different levels, it does them as a regression. So it makes life an awful lot easier, because then you only have to have one bit of code that will do all of the stuff for you. But conceptually, that's what it's doing. So ANOVAs are a form of regression. They're just a very specific form where you replace the level with the mean of those levels and then perform the regression. And the two-way ANOVAs and so on are putting in another term for that second one, so it becomes a sheet of paper that you're trying to fit your data to, and so on. And it gets 3D ones I can almost cope with. As it gets more, you've got to start thinking in silly numbers of dimensions. They're called manifolds, and it becomes really quite weird. But so if you think of ANOVAs as just doing this, fitting a sheet of paper, fitting a line to the data, I find it much easier then to interpret what's going on, because I'm just thinking, is there a slope that matters? Is this slope, which we've set to be a slope of 1, but is it statistically significant? So is there a relationship? So regression and ANOVAs are the same thing. They're both looking at, is there a relationship between an independent like variable, which here we just happen to have given this a name, A, and we happen to have called this level B. But that's all we've done. We've given it a name rather than its number. Okay, so what we have is the same result as the ANOVA. And if you think this is for the one-way ANOVA case, and then if you compare that with your notes, you'll find that this thing, r squared, is going to be the sums of squares that you can account for from your levels, so the sums of squares of the regressions. Okay. And as with regression, the same laws apply with the ANOVA. Now what we've been referring to as the IIDs, the ANOVAs use a pooled estimate of the error variance. They're assuming independent and identically distributed IID distributions over the predictor value. Regression is doing exactly the same. It requires that you have independent and identically distributed variables. And you need to check for those error deviations. And the way that we do that, and you can do the same in ANOVA, of course, because it is just regression, is look at the plot of the residuals against the x value. So to check for IID, what you want to do is look at the residual, the distance from the regression line to the data point, that error term, as a function of x. So here's one of those scatter plots that I showed earlier. its correlation and covariance is very close to 0. And that's the line, and it does have a tiny, tiny slope on it that corresponds to those data points. Okay, so that's non-significant, and you'd go, right, that means that there isn't a relationship. When you look at the scatter plot, you can see that there is. And if I plot that as the residual, so the reason for having this example with a flat line is so you can see the distance from the line to the data points, and there you see a clear trend. Okay, and all that's telling you is that your assumptions for the regression don't hold. The assumptions, for the ANOVA, the residuals of the ANOVA could be up here, down here, and up here. You'd be going, I can't talk about the ANOVA. It doesn't make sense because my estimates of this error variability, the distance from the mean, don't hold. And that's actually the one thing in ANOVA that matters. It should be all clustered evenly and equally about the 0 point when you look at it in terms of residuals. Okay, and I talked about the Kolmogorov-Smirnov. The last lecture of the module, I'll talk about some more methods for looking for normality, for checking these things. They are all inferior to looking at residuals. The trouble is that looking at residuals, there aren't formal ways of doing the statistics that your eyes do automatically and effortlessly. Okay, but look at them, they'll tell you if you're okay. The most common one that we see in psychology is known as the devil's triangle. As a variable increases, most commonly we see this with reaction time, what we see is that the variability of the dependent variable about that point increases. There's a relationship between the mean of reaction time and the variability of that reaction time. In terms of residual plots, it looks like that, and you can see there's a sort of triangle, hence the name of it. That the variability of the residuals increases as the predictor variable increases. This means that you are not doing, you haven't met the IID assumption. It means that your ANOVAs, your regressions, your t-tests, all of these things no longer hold. The significance value is not what you think it is. It's the estimate of something very different. Okay, so when you see that, you will have to do a transform, a way of getting it so that you get rid of that shape. And part of the things that you'll be doing in the last week, so between the poster and the individual write-up, is reanalyzing the data, because all of you will be collecting data which will have some violation of it, of the assumptions necessary for ANOVA. I don't expect you to do those analyses for the posters, but I will expect you to do them for your individual write-ups. This is why all of you will need to be able to do the analysis stage of your data sets, because you will all need to do them to do your own transforms and reanalysis of the data. Those of you who are using Cog demos, the transforms are there, you just select which one to do and click on the same buttons as you do for the normal analysis. Okay, but that's a very common pattern that you will see in psychological data, and we should be doing something about it. Okay, so regression is a natural extension to the correlation, which is an extension of the covariance, the standardized one, and it uses the slope and intercept. ANOVAs, t-tests, all of these things are part of regression, and at least I find it much easier to think about ANOVA as a regression, as how these things vary with each other. But you need to think about if that makes more sense for you or not. If you just like to think of the different levels and the different aspects and the interactions as being just that, discrete events, then think of it like that. I find it easier to think of the whole thing as just being a plane, just a shape that you're putting into the data. Okay, and check these residuals. Just look at the residual plots and see what they're like. Okay, It's a remarkably simple way of checking the core assumptions of regression and hence of ANOVAs and t-tests and so on and so on and so on. Is just to look at the residuals. If you don't see a pattern to them, if you don't see a devil's triangle or some, they narrow down in the middle and then get very wide. So if they're a band that runs evenly across the zero line, then you're fine. You don't needn't worry about other assumptions because the IID is the core assumption of least squares. And there's the summary of the entire lecture. Okay, so we're looking at how two variables change together. Okay, it only looks at the linear relationships, so use scatter plots. Okay, always think of the third variable issue. Covariance is the sum of the cross products. Okay, positive if the values increase together, negative if they decrease. The correlation coefficient is standardized covariance. Okay, and you're asking, does the observed covariance differ from zero? Well, standard ways people talk about it, and indeed I do, is a correlation. What we're really doing is a test of whether the covariance is different from zero. Okay, we're just using it as a standardized form. And for some reason, over time, that's disappeared as reporting covariance. And now we just talk about the correlation coefficients. Okay, I talked also in this about the confidence intervals and how you calculate them, how you can put them in as well. Give the reader the ideas of where you think the population value falls. And the non-parametric ones, the rank-based, straight rank-based to the Spearman's rank correlation coefficient. Okay, that's only really viable if you're measuring things on a continuous scale. So nice data, let's call it. But it's just clearly non-normal. Then the ranking gets rid of outliers. Basically, it scales everything. The concordant pairs techniques, Kendall's tau and Goodman-Kruskel gamma. They're the ones that with questionnaire data should be used. This one is rarely used, occasionally this one. Everyone opts for that and they shouldn't be. Regression is just quantifying that relationship. It's a straight line through the mean. Remember, it's the mean of the pairs, the XY mean. And the slope is minimizing the error variance. It's a least squares approach. Check the residuals. And if you just get into the habit of always looking at the residuals, you can plot them out in SPSS. And then it's done. It's fine. Okay, herein endeth the lesson. Just a reminder, there is still one group who has not resubmitted their ethics material. Please do so. You need to have a thing that says, an email from me that says, I approve your study. And other than my little signature bit at the bottom, essentially nothing else in it. Otherwise, you should not be running your studies. Hopefully you are all set. If you're set and ready to go, if you can come in a little bit earlier, then you can actually set up. So this afternoon you can collect data from people and we'll just get people running through steadily. We'll be able to use, I need to double check if the downstairs cluster is available. I'll be working with you there to try and get your setup, your study ready to run, because you really need to be running it. You can run participants down there during the week. This room is pretty much booked the entire time. It's relatively free after 5 o'clock, but you need to be getting data. Okay, because next week we'll be around. We can help you with the analysis of it. Numbers of you have got relatively simple analysis. Sometimes it'll get a little more complex. We'll be there to help you do that in the same way that I'm sort of always around to help you get your study put into cog demos to E-prime, however you want to run it, but it needs to be done. So we need to get a move on so that you've got time to analyze the data and make your posters. There are things on Moodle about posters. There's an example. Again, it's been chosen as not a particularly good example. I want you to have to think about what makes a good poster. Okay, it's not that hard. It's just a bit of common sense. But you should start to make the poster following the guidelines that are in the handout that I went through in the first lecture and that are still on Moodle. Look at last year's ones and their generic feedback. Try and improve on how they did the performance last year using their generic feedback. That'll give you indicators of the sorts of mistakes that people made One of the best ones last year, I actually had to wear sunglasses to look at it because it was, boy, was it brightly coloured and clashing, contrasting colours. In other words, it wasn't a very good poster because you could barely read the text underneath it, and it wasn't me being silly, it was very hard to do. Very colourful, not a good poster. Okay, so you need to start thinking about those. So always keep one step ahead of what's coming up there, so that as you're having to do it, it is not trying to do a poster in a couple of hours, because it will end up looking shabby. It won't have the right information on it. Okay, so that's it for today. I will see you this afternoon. I'll be in here from about